Hi, welcome to the Olympiad geometry. Let's continue our study on the geometry triad. Today we're going to talk about the generalization of the Menelaus theorem. In the past, we already learned about the Menelaus theorem and we learned about the problems related to the Menelaus theorem. So today we're going to talk about the generalization of the Menelaus theorem, which is another dimension of the learning. So we've learned about the first angle form of the Menelaus theorem. Let me just do a quick review here. So the first thing is about the Menelaus theorem. It says that if we have a triangle ABC and we can find the points on the points DEF on the line ABBC, AC respectively, right? We have 3 points here. And assume we have, for example, DEF 3 points, and the DEF are collinear if and only if AD to DB times BF to CFC times CE to EA equals to 1. Okay, that's the Menelaus theorem and the converse of the Menelaus theorem. And for the first angle form, that is same sine angle BAF to sine angle FAC times sine angle CBE to sine angle EB A times sine angle ACD to sine angle DCB equals to 1. Okay, that's the first angle form of the Menelaus theorem. And now we look at the second one. The second one is saying that let A prime, B prime, C prime be the points on the line BCCAAB of the triangle ABC, and O is a point not on the lines, not on these 3 lines, right? Then A prime, B prime, C prime are collinear if and only if this one. So let's draw the figure. First, we have the triangle here, A, B, C, and this is A prime, B prime, C prime, right? And O is another point out of these 3 lines, out of this line, and this line. Let's call it O. So we connect AO, C prime O, BO, B prime O, CO, A prime O, right? You should be already familiar with this. Directly write it down, right? Because we already know that if the C prime, B prime, A prime would be collinear if and only if AC prime to C prime B times BA prime to A prime C times CB prime to B prime A equals to 1, right? Then, based on this, we know that basically we can translate or transfer these segment ratio to the triangle area ratio, which always have the lines as AO times the C prime O to C prime O times the BO, which is basically the AO to BO. Similarly, for the BA prime to A prime C, that would be the BO to CO, right? The next ratio would be CO to AO, then all the AO, BO, CO are cancelled, which means it's just a sine angle AO C prime to sine angle C prime OB times the sine angle BO A prime to sine angle A prime OC times sine angle COB prime to sine angle B prime OA equals to 1, right? This one and this one are identical, right? BOA prime, BOA prime, A prime OC, and COB, B prime OA, AOC prime, AOC prime, C prime OB, right? So that's the second form of the Menelaus, second angle form of the Menelaus theorem, but it's just another expression, but I don't think really it's very helpful in the solving the problems. But anyway, it's just a knowledge here. Okay, theorem 1. If line L intersects closed polyline ABCDA on P1, P2, P3, P4 with a line AB, BC, CDDA, then AP1 to P1B times BP2 to P2C times CP3 to P3D times DP4 to P4 equals to 1. Okay, so we can think of this like we have 4 segments and we want to use 4 segments to form a closed polyline, which means we have several ways to form it. Right, A, B, C, D. That's the first way, and then A, B, C, D. That's the second way, right? And then A, B, C, D. That's the third way. Okay? A, B, C, D. That's the third way. So we have a line that intersects the closed polyline, which, each line of the edge of the closed polyline, right? So this would be P1, and this is P2, this is P3, this point is P4, right? So we want to prove that AP1 to P1B times BP2 to P2C times CP3 to P3D times DP4 to P4A equals to 1. Right, we want to prove this. And just look at the triangle ABC. Okay, triangle ABC and this line. So we have, let's call the intersection point of AC to this line, right? So P4, rewrite it, P4 is this point, right? And for this point, let's call it E. So for the triangle ABC and line L, we have AP1 to P1B times BP2 to P2C times CE to EA equals to 1, right? And for the triangle ACD and this line, we have, because we want to cancel this one, so we write it as AE to EC times CP3 to P3D times DP4 to P4A equals to 1, right? For this one and this intersection. So AE to EC, CD, CP3 to P3D, DP4 to P4A equals to 1. And we multiply these two equations, then we get this one. Okay, let's consider about another case here, but it's actually the same. I just want to show right, we have P1 here, and for BC, this point is P2. For CD, this point is P3. For DA, this point is P4. Right, this is P2. So it's the same. just connect the AC and meet this line on a point. Let's call it E. Right? For the triangle ABC and this, for the triangle ABC and this line, we have CE to AE times AP1 to P1B times BP2 to P2C equals to 1, right? And for the triangle CDA, for the triangle CDA to this line, right? Triangle CDA and this line, because we want to cancel this, so we start from A now. AE to CE times CP3 to P3D times DP4 to P4A equals to 1. Right, we multiply these two, we can see that CE to AE cancels with AE to CE, and then the rest of the part is equations that we want. Okay, that's for the 4-segment closed polyline, and then we can generalize it just because we already learned about the 3 segments case, which is a triangle case, and the 4 segments case, which we just proved, right? So if we generalize it, then we know that if A1, A2, A3, all the way to An-1, An is a closed polyline formed by n segments, right? That intersects a line L, and intersection points on line A1, A2, A2, A3, A3, A4, all the way to An-1, An, A1 are P1, P2, all the way to Pn. Then we have this one, A1, P1 to P1, A2 times A2, P2 to P2, A3, all the way to An-1, Pn-1 to Pn-1, An times An-Pn to Pn-A1 equals to 1, right? So we want to prove this one. Here we can just use mathematical induction, which means that we should be very careful of this, right? We use a mathematical induction, which is that we know the equation is valid if n equals 2, 3, and 4, right? Now we can assume that the equation is valid from 1 to k, right? From 1 to k, it's valid, or 1 to n. Now n equals to k, it's valid, right? So we want to prove the n-1 case, or k-1 case, right? You can think about that we have the n points, right? N points A1 all the way to An. N points on the plane, and now we want to have another point An-1, 0, right? Which means we just need to connect the An to An-1, and then connect it back from the An-1 to A1. So you can see that we didn't use a line A1, An, but let's keep it there, right? And we know that the line L intersects An-1 on a new point, which we can call it Pn-1, right? So we can see the 1 P1 2 actually here let me use K. Okay, let me use K, that's more clear. Let me use K. So A1 P1 2 P1 A2 times A2 P2 to P2 A3 all the way to AK minus 1 PK minus 1 to PK minus 1 AK times AK PK 2 PK A1 equals to 1. Right, this is valid. We know that it's valid, right? And we know that the line meets A1. Wait, no, the line meets AK. AK, the line meets with AK plus 1 on the PK plus 1, this point, right? So we don't know that the line meets with A1 AK plus 1. Wait. Something wrong. I see what's going on. Here is a trick. See, let me explain. If we use this system that's used adding a point, right? It would be very confused because now the P minus 1 point, now the PK minus 1 point should be, or let's say in the previous system that from A1 to AK, right, we have P1 to PK, which reference to A1, A2, all the way to AK, A1, right? And if we want to use a minus 1 point, sorry, we want to use a plus 1 point, add 1 point here, then we have the new sets as A1 to AK plus 1. Let's actually put it here, AK, and to AK plus 1, right? Then we have P1 all the way to PK and PK plus 1, right? Then we have it represent for the intersection point from A1, A2 all the way to AK plus 1 and AK plus 1 A1. See what's the difference of these two? For the point PK, in the first set, it represents for the intersection point with segment AKA1. And for the second one, it should represent for this one. So that makes a confusion here, right? So let's use removing 1 point. Okay, no, I'm not saying removing one. I'm actually want to say that let's use a system that we assume the equation is valid from 1 all the way to n minus 1. Okay, we already have n points here, right? So that means we just need to add a point, right, that connects from n minus 1 back to A1. Okay, so it's valid for the points that from A1 all the way to an minus 1, right? But we have the endpoints that we have a endpoints here. And P1 all the way to Pn still represents for what it meaning, right? Then we just know that for the closed polyline A1 to An minus 1, we have a line that A1, An minus 1, which have a intersection point with line L, but we didn't mark it, right? So let's mark the intersection point as E, for example, or B, for example, right? Then we know that we have the equation, because this from 1 to n minus 1 is valid, then we have the equation A1 P1 to P1 A2 times A2 P3 to A2 P2 to P2 A3 all the way to An minus 2. Well, we don't need, right? An minus 1, Pn minus 1 to Pn minus 1, A1 equals to 1. This is true. No, not this one, right? Because Pn minus 1 represent for the point from An minus 1 to An, right? Pn minus 1 represents a line, the intersection point of the line An minus 1, An, and the L, right? Which An should not be occurred in this equation. So the equation should be A1 P1 to P1 A2 times A2 P2 to P2 A3 all the way to An minus 1 B to B A1 equals to 1. Yeah, that's the correct equation, right? This is correct. And now we can use the Menelaus theorem to the triangle An minus 1 An A1, right? Which we have, because we want to cancel this one, so we have A1 B to B An minus 1 times An minus 1 times P n minus 1 to Pn minus 1. Oh, this is not time, right? That's represent for the segment An minus 1 Pn minus 1 to Pn minus 1 An times An Pn to Pn A1 equals to 1, right? That's for the triangle and for the using the Menelaus theorem. Now we multiply these two together, and we know that this cancels. Then we have, from there we have An minus 1 to Pn minus 1, and this one just to prove that if n minus 1 point is valid, then n points, the equation is valid, right? And now you know that we can push n to all the integers, right? Okay. For the theorem 3, let DEF be the points on the line of edges formed triangle ABC, right? So we have triangle ABC here. We have triangle ABC here, and we have DEF here. Right, and we know that AD to DB equals to lambda 1, BE to EC equals to lambda 2, BE to EC, and CF to FA equals to lambda 3, CF to FA equals to lambda 3. Then we want to calculate the area ratio of triangle DEF to triangle ABC. We want to calculate the area ratio of this triangle to this triangle, which can be rewritten as 1 minus the area of triangle ADF plus the area of triangle BDE plus the area of triangle CEF to the area of triangle ABC, right? And for the area of triangle ADF to the area of triangle ABC, right? Let's just write it down here. So we know that the area of triangle ADF to the area of triangle ABC can be written as, right, AD to AB times AF to AC, right? And we know that AD to AB is lambda 1 to 1 plus lambda 1, right? And times AF to AC, right? AD to AB, that's the area of this one to this one, right? And AF to AC, that's the area ratio of this one to this one. So we got the area ratio of this one to this one. AF to AC, which is a 1 to 1 plus lambda 3, right? It equals to lambda 1 to 1 plus lambda 1, 1 plus lambda 3, right? Similarly, we can get, well, if you just look at this form of the equation, then we directly know that we can have this one, the triangle DEF to the area of triangle ABC equals to 1 minus C lambda 1 to 1 plus lambda 3, 1 plus lambda 1. Then the next one would be, well, I would like to write it as this way. Lambda 2 to 1 plus lambda 1, 1 plus lambda 2, plus lambda 3 to 1 plus lambda 2, 1 plus lambda 3, right? So it equals to 1 plus lambda 1, 1 plus lambda 2, 1 plus lambda 3. 1 plus lambda 1, 1 plus lambda 2, 1 plus lambda 3, minus lambda 1, 1 plus lambda 2, minus lambda 2, 1 plus lambda 3, minus lambda 3, 1 plus lambda 1, right? That is the final answer, which is 1 plus lambda 1, 1 plus lambda 2, 1 plus lambda 3. The top would be 1 plus lambda 1, lambda 2, plus lambda 2, lambda 3, plus lambda 3, lambda 1, plus lambda 1, plus lambda 2, plus lambda 3, plus lambda 1, lambda 2, lambda 3, right? That's the first one. And minus, the rest of the part would be minus lambda 1, so this is gone. Minus lambda 1, lambda 2, this is gone. Minus lambda 2, this is gone. Minus lambda 2, lambda 3, this is gone. Minus lambda 3, this is gone. Minus lambda 3, lambda 1, this is gone. Right? So the rest of the part would be 1 plus lambda 1, 1 plus lambda 2, times 1 plus lambda 3, and the top is 1 plus lambda 1, lambda 2, lambda 3. Okay. That's the conclusion. Okay. So based on this, in above case, if lambda 1 equals to lambda 2 equals to lambda 3 equals to p, then the area would be this one. It's obvious, right? Because this would be 1 plus p to the power 3, which can be factored as 1 plus p times this, and we cancel a 1 plus p term. Then we get this one. And conclusion 2, if AE, BF, CD are concurrent, then we have this one. So what happens if AE, BF, CD are concurrent? That means lambda 1 times lambda 2 times lambda 3 equals to 1 based on the Sylvus theorem. So on the denominator, it is 1 plus 1. That is 2. Denominator doesn't change. Okay. So in this video, we shortly expand the Menelaus theorem by generalize the Menelaus theorem to the closed polylines. And I think this sometimes can be useful. I hope you like this video. See you in next one. Well, if you like this video, please click the like button, comment, share, and subscribe to the channel. Okay, see you in next one. Thank you.